I want to start with thanking the organizers of this conference. I really enjoyed it, even if in Hawaii the time difference is really hard. But it was really nice to be able to attend to this conference. So I'm Sebastien. I work on the SCExAO instrument at the Subaru telescope. I'm a part of a team that is composed of 6 people in Hilo, Hawaii, that are on the top of this slide. But we collaborate with many more people, as you can see here, that work on different instruments and modules and collaborate with us on things that I will talk about right now. So SCExAO is a high contrast instrument. It's located on the NASMIS infrared focus of the Subaru telescope. And it gets a partially corrected wavefront from AO188, which is the adaptive optic facility of the Subaru telescope. And so SCExAO is right here, and it's composed by 2 different benches. One that is in the infrared, that gets the light from 900-ish nanometers to 2.5 microns, and a visible bench on the top that gets the light from 600 to 950. And both these benches are on the top of a hell of electronics and cables and things like that. So at the origin, the core of SCExAO, the idea is to have an extreme adaptive optic system that relies on a pyramid wavefront sensor working in the visible between 800 nanometers and 900 nanometers. And this pyramid controls a deformable mirror, a 2K from Boston deformable mirror that can run up to 3.5 kilohertz. And that allows us to reach a trail ratio of 80% in H band. SCExAO is also composed by coronagraphs to suppress starlight and do the study of closed circumstellar environments. And so that's the basic idea of SCExAO, but over the last 10 years, there's a lot of things that were added on the top of that, as you're going to see on this little animation. So this was the first SCExAO bench in 2009, and in 10 years, there was a lot of different modules and new things to test that were added to that. And so now it's way more complicated. To talk a very little bit about science, SCExAO has 3 different competitive commission science modules. The first one is CARIS, which is an integral field spectrograph working in spectral bands J, H, and K, whose aim is to characterize and detect exoplanets and disks. We have the Vampires instrument. It's 2 cameras in the visible that can do differential polarization imaging or H-alpha imaging. We can also do direct imaging, as you can see on this very nice high-strail image of the Capella binary with a 40 milliarc-second separation. And finally, we have the REACH instrument, who was designed to do post-coronographic injection of the companion light into a single mode fiber, which is directly connected to a high-resolution spectrograph named IRD. It's a facility instrument in Subaru telescope. And so doing that, as we can see on this little test that we did on HIP 18413, we can do high-resolution spectrograph up to a power of resolution of 100,000. But so even if we have these fancy and nice instruments, we still face the same instrumental limitations that garbled us during this week. So island effect and non-common path aberrations. I'm not going to talk too much about that because everyone knows them. The idea here is that the modularity that we have with SCExAO allows to easily integrate and test on-sky wavefront sensing and control techniques, because we have a lot of cameras in different wavelengths. We have cameras in the visible. We have 2 CRAD 2 cameras in the infrared. We just received and installed a CRAD 1 in the infrared. We're going to commission a MKIDS detector in the infrared as well. So there's a lot of things that can be tested here at Subaru And there have been a very strong collaborative effort to push the limitations, the instrumental limitations that were created by those island effect or NCPA problems. And so right now I'm going to list to you several, I cannot list them all, but I'm going to list several of the wavefront sensing solutions that were tested on SCExAO. The first one that I want to talk about is the Zernike asymmetric pupil wavefront sensor using asymmetric pupil mask to do some fast retrieval with the focal plane image. This work was done by Mamadou in 2018 and was tested on Sky. And as you can see right here, this algorithm was originally designed to correct for the low wind effect. And so it was tested on Sky, and you can see the difference between the open loop and the closed loop. The PSF is way more symmetric, and there was a gain in trail of 37%. And right now, as we heard during the first day of this conference, Colin Lopez is now working to cover this algorithm, is working on it to improve this technique. The second thing that we're investigating is using a linearized analytic phase diversity algorithm that was originally designed to work on the co-phasing of segmented apertures, but that was adapted to the Subaru telescope and more particularly to correct for the low wind effect that creates piston tip tilts in the 4 quadrants. We did some tests on the bench with an internal source. The idea of this test is to apply a static low wind effect like phase map on the deformable mirror and try to correct for it with a closed loop control on the two vampires cameras that are in the visible. So one of the image that the algorithm takes is a focal plane image, and the other is a defocus plane image. So as we can see on this loop closure right here from loop iteration 0, where we can see the aberrated PSF, we can see that as the iterations are going on, the PSF is reconstructed, the aberrations are corrected, meaning that we managed to correct for the low wind effect with the LIPD algorithm. And so now we are waiting to have some time on Sky to test that. Another algorithm is developed by Mason Lamb, and it's a monoplane phase diversity that takes a defocused image that was tested in the infrared on the infrared camera. And so it's the same idea as for LAPD. We apply a static map on the DM, and this time Mason was trying to do open loop estimations of the wavefront. And so we can see here a random piston tip tilt applied in each of the quadrants of the Subaru pupil. You can see the PSF that is associated with this phase map. And you can see that his algorithm actually did a pretty good job in estimating this map. You can see the difference right here. It's pretty small. So this was done on the internal source, and we now need to work on some on-Sky data that we have to validate this algorithm on Sky. The other algorithm that you heard about during this week is the Fast and Furious algorithm, the sequential phase diversity implemented by Stephen Boss on the SCExAO bench. I'm not going to talk too much about it because he's going to talk a bit about it later during this talk, but basically Stephen managed to validate this algorithm on Sky with various seeing conditions and managed to correct for the low wind effect that was either created naturally in the telescope or that was introduced, as you can see right here on the C image, that we introduced directly on the DM, even on Sky, to show that it was working. This technique that I'm showing right now is a neural network approach to do a PSF reconstruction from the pyramid wavefront sensor telemetry. The idea here, led by Barnaby Norris in Australia, is to basically train an algorithm by providing to it synchronized telemetry from the pyramid wavefront sensor and a focal plane image. The idea is we want this neural network to be able to predict what the PSF will look like just by looking at the telemetry of the pyramid. And so we can see a little test on Sky here. On the left, we have the input image, which is the pyramid telemetry. On the right, you have the truth image, and in the center, you have the predicted image by the algorithm. So you can see that it's doing a pretty good job to estimate what the image should look like. So again, this was tested on Sky, and we still need further tests to characterize the algorithm. And the last algorithm I will talk about was presented yesterday by Noor Skaf, and it's basically reinforcement learning. Basically, the idea is to change the reference of the pyramid while the AO loop is running to correct for non-common path aberrations. And yeah, finally, I just want to give a quick word about that, even if it was also mentioned during this week. We are also trying to investigate the idea of an interferometric and photonic approach to wavefront sensing. The idea that, as you can see on the right, is you have a single telescope and you can sample the pupil by dividing the pupil into a microlens array. And that allows you to do relative measurements of the phase between the subpupils. If you add that, if you couple that with a spectrometer, with a spectrograph, you have the possibility to have phase measurements as a function of the wavelength, which is pretty interesting and pretty critical for example, fragmented or segmented pupils, because it can allow you to tackle down the island effect by measuring the differential piston between the quadrants. But also for the future segmented telescope, it could help you do some kind of fringe tracking, or co-phase the telescope. So on SCExAO, as Barnaby and Kevin showed during this week, we have several modules that are used to investigate this. We have the glint module, the photo lantern, and the first module. So all these efforts, all these techniques their tests were facilitated by the fact that SCExAO is a nice test bed for remote collaborators. First of all, SCExAO can be online 24 hours a day, 7 days a week. Basically, what you have is all the computers are possible to be accessed through VPN, and you can access to VNC viewers that allow you to control the instrument. So here, for example, you have the VNC viewer for the main control of the instrument to control the main feature of the instrument. I will talk a bit more later in details about this. And then every user can have its own VNC session, their private VNC session, where they develop their algorithm and their code. So the way it works, each new user who wants to try something on SCExAO get trained by someone from our team to operate the instrument with what they need. And then once they're trained, they can by themselves log in onto SCExAO computer and try to test their methods. We have a way to coordinate all these tests through a Slack channel. So we have a bench Slack channel where people can ask if the bench is free, if anyone needs anything on the bench. And we also have an online calendar where we can plan to do some long tests, for example, or short tests, or we can also log in this calendar, the summit works. And there's always someone, because we have so many collaborators around the world that are using SCExAO, there's always someone to answer a question or to troubleshoot someone on the Slack session. So it's usually pretty fast to be debugged, to be troubleshoot on a software level. And if there's an issue about the hardware, it can be a little bit longer because it requires the team in Hilo to drive to the summit, but it's doable. And once you're ready to go on Sky, well, you can use one of our engineering nights. We usually have around 7 per year to test and validate your method. So now we're going to do a live demonstration of SCExAO, but first I'm going to walk you through this screen that you're going to see. So this is the VNC that you use to control the main features on the instrument. Here you have the status of the bench. So as you saw, the optomechanics of the bench is pretty complicated. There's a lot of cameras, there's a lot of filter wheels and things like that. So all the status of all the motors and filter wheel are repertoriated in English, yeah, repertoriated here. You also have a GUI if you want to do some chronograph alignment, and you can see the list of all the chronographs that are available on SCExAO. You have a camera to see the status of the pyramid wavefront sensor. This is the DM channel monitoring. Basically what it does, you can basically write on different channel, on 12 different channels. And in the end, all these channels are added together and combined and showed in this channel right here. And the one below is just a voltage map. We also have a shared memory monitoring to see if all the cameras are working well. We have these two infrared internal camera viewer for the C-RAD 1 and the C-RAD 2, and basically two terminals to control the SCExAO bench. And so now we're going to connect with Steven from the Netherlands, who is going to log in live. You hear, Steven?
Yes, I'm here.
All right. So now we're going to switch to here. First, as we do always, we say that we're going to use bench on the Slack channel.
Yeah.
And then we can go here. And Steven, you can go ahead. Steven is going to log in and set up the instrument to test the Fast and Furious live for you.
So yes, so I'm also logged in on a VNC viewer, and I'm not sure if you can see a mouse right now.
It's not me.
So I will just, this is basically to show how easy it is that in a few steps you can start using the instrument and do your tests. So the first thing that we're going to do is we're going to turn on the source so that we can actually see a PSF. And then we're going to use the Chuck, the C-RAD 2 detector that is shown over here. So right now, the window size is pretty big. We don't need a big window size for Fast and Furious. So we're going to make it a bit smaller. So we're going to take a look at the help function. So we're going to want to have a 64x64 window. So let's change it right away.
So yeah, all these commands that you saw appear is when Steven clicked on H for help on the camera. It shows you all the things that you can do with the camera. You can change filters, you can change the exposure time, you can change the size as he does right now. You can acquire darks, you can remove the darks and stuff like that.
Yeah. So now the camera is set to 64x64 pixels, but it's running at 9 kilohertz right now. That's a bit too fast. We don't need it. So we're going to lower that to something like 2 kilohertz. This is 5. And this is 2. Okay, so let's take a new dark to make sure that's all done. So as you can see right now, the PSF looks kind of ugly. And this is because the DM is at this point not in its flat state. So let's do that first before we continue. So we're going to go to the control of the RTC, and we're going to say, make the DM flat. And I'm actually mistyping this, so let's correct this. Okay, I have a little bit of lag, so let's see if I'm actually removing, the correct letters. Okay, so now the DM should be flat. Press enter. It's a little bit slow.
Yeah, and you can see the shared memory monitoring in this window right here. You can see, for example, the IRCam 0, which is this camera that is currently running at 2 kilohertz. And the DM flat didn't apply.
Yeah, so I'm not sure what happened there. Let's.
It's the law of the demonstration.
Yeah, I guess. So in the meantime, we're gonna put some more flux on the detector. So we're gonna change the filter. So right now, as you can see in the upper left corner, there are many filters in. So we're going to remove one to put in some more flux. Source filter. I'm forgetting all the commands. Should be source flux and then filter, and then we're going to set it to 1. Okay, so that's a bit more light. So now we're using the full H band, and we don't need that. We want to go actually for a narrowband filter. So let's go to the 25 nanometers. Let's go there. Yeah, there it is. Okay, so now the question is actually, Sebastien, why we don't have a flat DM?
That's a good question. Let me check.
What I can also do is I can just start running Fast and Furious. That should also activate the DM, right?
Yeah. You will get your own flat.
Maybe I can start with that. That's very easy.
Yeah. Go ahead.
Okay, so I'm running Fast and Furious right now from another window. And that is not helping.
Okay, guys, we are at 5 minutes after. So while you debug the system, probably we could take some questions in parallel. So there is one by Mamadou to Sebastien. So yes. Mamadou, could you please ask while Steven works on the experiment?
Yeah, sure. Thank you very much. I can see that the DM is now flattened. So
yes,
cool. Great news. I just remember that I think the first time I used Slack was with the SCExAO group 2 or 3 years ago. So it was one of the great ideas that I could find apart from all the scientific things that we can do with SCExAO. I have a question for you, Sebastien. So you mentioned the high dispersion coronagraphy, and I was wondering, are you using a fiber-fed IFS? Or
no, we just have we have a fiber module that is in the focal plane after the coronagraph, and we just put the single mode fiber on the planet, and it goes straight to the high resolution spectrograph.
So you're just sending the signal of the planet to the fiber, right? Mm-hmm.
Yes, so exactly. Actually, it's not only one fiber; it's multi-core fibers. We have 7 fibers. 1 in the center for the planet, and 6 on the sides for the speckled light, for the starlight.
Okay. So
and thanks to that, we can
you could do some kind of molecular mapping since you have several fibers in the image plan, right?
Well, the idea is for now to do a subtraction of the stellar spectrum to the planet one to retrieve the spectrum of the planet, and hopefully find some features in the spectrum.
Yeah. Mm-hmm. Cool. Thank you. Very nice presentation.
Thanks. And so I think Steven debugged. I don't know what happened with the DM, but so you can see that he did add some low wind effect mode on the channel 7. And Steven, maybe you can just run it real quick.
Yeah, I'm running it right now.
So we can see that the PSF is going back to normal, so proving that Fast and Furious is working. And so, that was actually the last thing that I wanted to say. I'm sorry for this little inconvenience.
Okay.
Just to say that SCExAO is a competitive science instrument, but we can also test a lot of things. There's exciting upgrades that are to come, and talk to us if you want to try new things. We can say no to things. I'm happy to take questions on Slack because I think we're running late.
Yeah, there are actually many questions. So Jérôme, could you please go ahead?
Yeah. So the question I had, is you simulate the turbulence with your DM, if I understood well, and I was wondering, let's say, I suppose your DM has let's say, a low order, so does not generate high spatial frequencies like Christophe Verino has shown might occur next to the spider veins. How do you expect this high spatial frequency to be managed by your algorithm? Do you expect some different behavior?
You mean the actuators right next to each other? Sorry, can you repeat the question?
I mean, the OPD will be actually showing spatial frequencies that the DM cannot correct. So you will have in your wavefront error a residual term, which is aliasing for some sensors, or I mean, producing something. So I mean, for your algorithm, how do you manage that?
Yeah. That's a good question. I never thought about that.
Okay, thanks. Yeah.
maybe. So it's not only like maybe you can manage those with higher order modes, because, for example, Fast and Furious or other phase diversity algorithm, they can also correct for high order modes in Zernike's, and so you can correct the wind effect modes with the basis of 12 modes, and then for the higher modes, you just add those Zernike's in your reconstruction.